So we'll start. Okay, this is going to be lecture 7 in the lecture notes. And the idea is to discuss non-adiabatic case a little bit more in details. So we looked at the Born-Oppenheimer separation, right? So that was the previous lecture. And right, so we have sort of a molecular problem. And then if we want, we could solve time independent or time dependent. There are two possibilities. They are really not that different from the algebraic point of view. Just the difference like in the treatment on the right hand side, it's either this or we can also do this stuff, right? So, and generally for dynamics, what is interesting, yeah, the time independent Schrödinger equation, this is time independent Schrödinger equation. This is for, I guess, various type of spectroscopies. Right, so the molecular Hamiltonian is H electronic plus kinetic energy of the nuclei. That's what we generally separate. What I'm sort of skipping, and today we'll be mostly looking at the vibrational part. So generally, when we talk about the electronic part is kind of straightforward. Electronic is you fix the, say, nuclear position in space, like if it's a hydrogen, oxygen, water molecule, say, yeah, you fix the frame, you have some sort of coordinate system for the nuclear positions. The nuclei are not moving anywhere, and we solve for in the same kind of coordinate system, we solve for the electronic variables, right? So this is the electronic structure problem. And that's what usually is done when you study molecules, they are fixed. And then you look at the electronic functions, mostly ground state. Then there is this parametric dependent electronic potential energy surfaces. And so I can vary problem. And this is done in programs like various electronic structure programs. It's like, to name a few, let's say Gaussian was one of the first. Gaussian is still going because the name comes from the Gaussian functions that are convenient to introduce the basis for the effectively this electronic function. Of course, you need multiple, you need multi-electron wave function to solve the problem. We're probably going to dedicate some time for this at the end of the semester because it's a very significant problem and lots of efforts went into solving it. It's not trivial, even though we separated the nuclei here as parameters, so we have the electronic variables to treat, but yeah, it's still a difficult problem. So Gaussian, QChem, there are lots of, these are commercial ones, and there are like games. This is the games has two versions, UK, US. One of them is free, another is commercial. I think the US is free and UK is not. So one can, games is commercial, QChem is commercial. There are a few others, the free ones. Well, in the age of quantum computing, people start looking at this problem, thinking about using quantum computer to solve it, and there are lots of free software that is done in Python. These guys are mostly Fortran codes because they are more efficient. But
Qtip.
Qtip.
No?
Yeah, maybe I don't know Qtip.
It's a Python like.
Python library. Okay, PyCF. That's what I remember. And then Python, yes, and things like, yes, there's another recent software block 2 for like a particular version of solving this problem with a density matrix synchronization group. Tequila, that's something that my group and Alan for Guzi groups is developing, but that's just for quantum computing mostly, and it's relying on so-called open fermion package. Fermion, and there are a few others. One can look and find them online, right? Because don't have everything, and it's still under development. But today we will sort of proceed thinking that, okay, someone solved this problem already, right, for us, and we will be kind of, we will be building on top of that, right, and we will return to that later. But the setup is that we have a frame in this problem, and we got the electronic functions, and I guess the two main products of this problem is electronic functions and electronic energies, right? And then we can go back to these problems, either time independent or time dependent, and solve them using the ansatz. For the ansatz is a German construction, right? So you can have four. Let me write for time independent. Usually the exact expansion is from 1 to potentially infinity. You have electronic functions, the basis. And at this point, the nuclear coordinates are not parameters anymore. You have nuclear coefficients to compensate for the fact that these guys depend on the big R's according to this equation, and this, like, you need an extra dependence on the big R's because it was not constrained to like a molecular problem, right? So these are like the coefficients that depend on parameters that were fixed initially. Now they are not fixed, but their dependency is determined by this equation rather than the total equation, which this function should be an eigenstate of, right? So that's why we need an extra function of the nuclear variables here. And then for the time-dependent case, the wave function is contained in a time also, and it still can be written as a linear combination of the same functions. These guys are always time independent, and then these guys are nuclear dependent and time dependent. Okay, and so okay, so this is like general framework. We wrote what are the equations for these guys, exact ones with non-adiabatic terms, with the terms where we act on the electronic functions using the kinetic energy operator. So this is state I and this is J, right? So we in exact formalism we have these, which are non-zero. And that's what separates exact formalism from the non-exact. The Born-Oppenheimer approximation is neglecting these terms. Essentially, it neglects the dependence of the electronic functions on the nuclear coordinates. Okay. So now I like to emphasize that this is Born-Oppenheimer separation to electronic and nuclear, but it's not yet an approximation because from here you can go to the exact formalism accounted for. It's just an intermediate step, right? So from here you can go to the exact formalism, or you can neglect these things and then it becomes like a Born-Oppenheimer approximation. So it's yet not the full story. And some people like to say that in this problem, the nuclei are treated classically. You can say that because technically they are like parameters, so they're just numbers put in this problem. But once you get out of this problem, then the nuclei become variable, and then there are multiple choices one can do. And those choices are quite actually different in nature. One choice I already said, you could either go adiabatic Born-Oppenheimer approximation, or go exact, which sometimes this expansion is called Born-1 expansion. But it's another way to say it's a kind of exact way of doing things without either this or that. I don't think people generally separate time dependent from time independent as long as there are multiple terms and you account for couplings. That's like exact treatment. But then second, within both actually Born-Oppenheimer approximation or exact, you could do quantum treatment, treatment of quantum nuclei, or classical treatment of nuclei, or semi-classical also is a possibility, and it boils down to the question of whether you leave for the nuclei the wave functions, or you decide to go to classical trajectories essentially, right? So those are they're usually called quantum classical methods in the case of the sort of treatment where it's multiple states, and like one of the famous methods like surface hopping or Ehrenfest dynamics. We can talk about them a little bit later, or once we discuss the full formalism. Okay, but there is also a nice way of connecting quantum and classical, and that's through path integral formalism of Feynman, because generally before Feynman path integral formalism, I guess classical formalism was introduced somewhat ad hoc, meaning that you sort of impose a certain equations of motions for classical nuclei. You substitute these functions by trajectories, right? And these trajectories, they go to the parameters of the electronic functions, and they also represent with the momentum second classical variables for the nuclei. And you just use Newton equations with some forces that are coming from the electronic states. And the reason we call that ad hoc introduction, because there is an exact formalism, of course, with these representations, and there is this, and there's nothing in between, right? So ideally, if you develop some theory which is approximate, you want to have a knob that can rotate between the exact and computationally kind of easy, right? That's a systematic improvement. You could systematically improve the classical into the fully quantum if the quantum effects are important, and these formalisms without the path integral formalism of Feynman, they were not able to do that. They either do this or that. There is nothing to it. But with path integral formalism, there are ways to connect this with this, and in a gradual fashion. And yeah, there are methods based on that. But that's probably kind of beyond this course. So you could study it on your own. Again, it's if you're interested in dynamics mostly. Okay, so from this, we could just go and study, okay, what will be the kind of certain features of time dynamics on the multiple surfaces, because this is somewhat an interesting problem, happens very frequently in the applications. Of course, the adiabatic dynamics is also interesting, but it's, I guess, less general, less complicated. Now, before we go there, I guess there's one thing to mention here. It's the representation that you will see very frequently in literature. So the representation of these guys, the potential energy surfaces, and these guys, the nuclear wave functions, because those are kind of main players when it comes to the looking at what's happening to the system. Since these are fixed, they are kind of obtained and assumed behind the scene. It's like a basis vectors essentially in the electronic subspace. But these potential energy surfaces, let's say if we look at the, usually in the coordinate system, there's a nucleus, and it's a multidimensional in general. That's why we call this things potential energy surfaces, electronic ones. But for very simple case of, let's say, hydrogen, with hydrogen, we dissociate two hydrogens, and this is the ground state curve usually, right? So where does it come from? It comes from this, and it's just a one solution. There is another solution, which is a excited one. This in the minimal basis, people like to call this is a sigma, and this is the sort of sigma star orbital, because in a sort of the atomic orbital picture, you have in the minimal basis, you have 1s orbital. That's now a solution of this problem. 1s problem, then let's say different s spin, you get this orbital sigma, and this one is sigma star. This is bonding, this is anti-bonding, and this is approximation to the electronic state corresponding to the ground state, later determinant with say two opposite spins, and gives state like this. And the one that is here, it's unoccupied in the normal, like ground state. They are unoccupied, but when we go to the excited state, they occupy double excitation from the sigma star, and then becomes sort of antibonding impulsive. And of course, this is the minimal basis picture. If you put more states, more basis functions, then there are other states, right? So the states of, if you work in the Hilbert space of 2 electrons, then there are potentially infinite states, considering that 2 electrons can just leave the nuclei and go somewhere else. It's like unbound states are possible too, H2 plus, so on and so forth. But this is a good picture to illustrate some of the physical solutions of this equation, time-independent Schrödinger equation, and especially in the Born-Oppenheimer picture. What happens is that later people start drawing the lines here. Those lines correspond to solving the time-independent Schrödinger equation with the E's instead of potential energy surfaces with the R dependence, right? So these are not really an energy levels, they are surfaces, they depend on big R. And these guys, on the other hand, are their kind of solutions of the vibrational problem, usually. Now, you may also wonder, the vibrations is not the only motion in of nuclei that can happen. There's a translational there is a rotational, vibrational. Those are the three typical motions of in molecules for the big R's, right? And where do these two go? When we start looking at vibrations, they assume to be separated because these electronic energies, they are not dependent on the translation, right? So the three coordinates of translation are not present in here, right? So you could change the coordinate system so that the big R's will be kind of internal coordinates that are moving with the molecular system coordinates, right? Plus, there is three coordinates for the rotation. Those are harder to separate because rotation inherently related to the vibration, right? So there is no exact separation. You could easily think if the hydrogen molecule rotate very quickly, right? So then there's a stretch because of the centrifugal force, right? So this is a classical analogy, of course. But even at the quantum level, if you try to separate the coordinates in the Hamiltonian, it's not possible to do exactly. So this course, since it's not a course in spectroscopy, we don't really go into these details, but just keep in mind that these translational coordinates can be separated exactly. These rotational coordinates can be separated approximately in the approximation of the rigid rotor usually. And then the couplings are sort of ignored. But in some situations of the floating molecules, vibrations and rotations are coupled, and things are not that black and white anymore. So what do you call rotations and what do you call vibrations? There's a row of vibrational couplings usually that some people study, but this is kind of in the old days when the molecules were studied in vacuum, people were interested in that. These days, people are more interested in materials, various organic light-emitting diodes, stuff like that. Their molecules don't rotate much, right? So maybe in the solution they do, but usually it's a vibrational electronic, say, problems. How energy goes from electrons to vibrations. That's kind of a big deal because if you lose energy from light, say to the vibrations, that's the heat, right? So that's the main source of heat. Although translational and rotational, they are also can be eventually can be used to deposit energy that will be a heat because it's in thermodynamics terms. It's not some sort of the directional motion that macroscopically changes macroscopic coordinate. It's the microscopic and it's chaotic and cannot be used to produce work, right? So that's why it's bad to have rotation and translations. Yeah.
How bad of an approximation is the trotterization method that we use?
Trotterization method, that's the method we use for solving a specific eigenvalue problem, right? So Trotter method is if you have a Hamiltonian, then you could produce the spectrum of the Hamiltonian by doing this with some state. Okay, and then since the typical way of exponentiating operator is diagonalizing operator, all right, but we don't know how to diagonalize this. So we break it down to the two parts, let's say for simplicity, two parts that we can diagonalize, right? And then we substitute this by AT and then minus PT, right? That's the Trotter approximation. So it has no relevance to the separation of variables. Okay, so effectively you have electron variables and nuclear variables, and both problems, electronic problem and the nuclear problem, they're both difficult, right? Meaning that there are Hamiltonians, let's say for the electronic one, that is not exactly diagonalizable. That's why to solve this problem, we could use Trotter approximation. Yeah. And to solve the nuclear problem, we also can solve, we can do Trotter approximation. Also, we can use Trotter approximation not to solve the eigenvalue problem, but to solve the dynamics problem. Because in order to solve time dependency shown your equation here, the formal solution is minus IH molecular T acting on the psi at the T equals 0 to produce the psi at the equal T, right? So it's some different T. So this exponential operator is called evolution operator. It's not, you can write it formally, and if you put this in the Schrödinger equation, it will solve it. But this operator, the problem is how do you construct it as a what do we usually use? We use some sort of vector representation for the function in some representation, and then this is becoming some matrix, but we don't know what this matrix is because we cannot exponentiate something that we cannot diagonalize easily. Okay, so that's why Trotter is one way to address that. It's not the way to separate variables. Right? Separation of variables is a different story. It's like if you have a Hamiltonian that depends on two types of variables, x and y. The idea is instead of solving the problem with two variables, somehow first do the separation and maybe approximately to the variable, to the Hamiltonian which depends on x and the Hamiltonian that depends on y. This simplify things, even though this Hamiltonian is not exactly solvable, you still may need Trotter to do each of them, but these are smaller problems, right? So that's why first, the general structure of an elementary quantum mechanics for chemists at least, it's breaking this big Hamiltonian to parts, right? And so one of the simplest part is to separate time, right? So you separate first time, you formulate time independent of your equation. Because psi here and psi here are different size, one has time, another doesn't. I'm just abusing notation by putting them the same sign. But keep in mind that they are like different size. So we separate the time, then we start separating variables. And translation can be separated just if you change the coordinate system, your total Hamiltonian becomes this Tn part is the kinetic energy of nuclei. It separates into the kinetic energy of the center of mass and the kinetic energy of internal nuclear motion, right? So you can go through this and separate, and the electronic part will not depend on the center of mass motion, right? Because simply it's just the momentum of the nuclei that will make the biggest contribution here. Okay. Now there are some issues which are quite interesting because technically, and that's a interesting problem for the say hydrogen atom. Technically, center of mass needs to be of nuclei and electrons, right? And so then there is a separation of variables. But if you start making the center of mass of the nuclei and electrons, then internal coordinates they also mix electron and nuclear, right? So that becomes messy because why is it messy? Because we would like to keep them separate, electrons and nuclei, because electrons are fermions. So we know a lot about their kind of symmetries of fermionic wave function. This, for example, is that if you exchange two coordinates, then the wave function needs to change the sign. With nuclei, with chi function, there's no such relation, unless, of course, you have identical nuclei with a sort of nuclear spin. So then there are possibilities like that, but they are well, not necessarily. All the nuclei could be distinguishable particles in your function in general for general molecule, but electrons they are indistinguishable. So therefore, we would like to keep them separated so that we can use symmetries. Like the symmetry is similar to like harmonic oscillator. There is a symmetry with respect to kind of exchange of x to minus x, makes every level either symmetric or anti-symmetric with respect to that. So here we could use so-called Slater determinants because this is a construction exactly for the anti-symmetry. And if we start using Slater determinants here, that would be a waste of resources because there is no symmetry like that there. So this is a long way to say is that separating the center mass of the electron and nuclei is not very good approach because it mixes things. And then people usually do separate center mass of nuclei just by themselves. So that creates a certain couplings in the internal motion. Because if you now consider the hydrogen, even hydrogen atom, then there is a coupling between the motion of the nuclei and electrons because electrons follow the nuclei, right? So, and technically, the hydrogen atom solution, the wave function, total wave function, can be written as a nuclear wave function of the center of mass coordinate for the both electrons and nuclei. And then the electronic function, which is the delta R, which is the distance of the electron from the center of mass corresponding to the center of mass of both electrons and nuclei. And so this is in the quantum information terms, it's not entangled state. It's a state that is a product state. Interestingly, if you rewrite this function in terms of decomposition of normal Born-Juan decomposition, where chi would be center of mass of nuclei, well, which is actually just a nuclei, right, in the case of hydrogen. And that's a different function. And then electronic functions with parametric dependence on the, well, like in the normal Born-Oppenheimer picture, where you have nuclei, they're fixed, and we're solving for electron, one electron here at the Rn. So then you actually need the whole decomposition. So it becomes not a product state. So this is a great example of one function being a product state and not product state, depending on the coordinate system that you chose. Okay. So the entanglement, quantum entanglement between the electrons and nuclei, it's a concept that depends on how do you choose the coordinate system. In this case, it's a very simple example showing that. This is just something to remember whenever people talk about entanglement. All right, so this is a long diversion from the main topic. Okay, so we separated translation and rotation in general, and the separations are somewhat complicated. I'm not going to go there, but it can be done. So let's focus on the 3n minus, usually what is left, and 3n minus 6 coordinates that are vibrations, and in the n is the number of atoms or nuclei, right? And it's 3n minus 6 for a general molecule, 3n minus 5 for the linear molecule. So hydrogen is linear. So if you put the 3, 2, 6 minus 5, 1 is left, that's the vibration, right? Vibrational case for the linear molecules, it's 3n minus 5 because you're losing a certain rotation, essentially because of the linearity and absence of the momentum there, angular momentum there. Okay, so if we go back to the hydrogen, this is the usual picture people draw, and these levels, they are usually found from the harmonic oscillator approximation. How do we get to the harmonic oscillator problem? It's just simply from the nuclear problem, where if we do Born-Oppenheimer, then it's this, let's say, particular state. We wrote this, and then it's I R equals to E chi R, right? So this is harmonic oscillator problem if this is approximated to the function of R as a E0 electronic I R0 say every of course every potential energy surface which is bound meaning that okay the nuclei here, this function here is bounded function. It's while here it's unbounded, so it's like a plane wave sort of thing. Here it's bounded because there is potential holding it, and so for the bounded cases usually there is a position where this function has a minimum equilibrium position. And then since it's a minimum, that means first derivative is 0. So this the first non-trivial part is the second derivative, which is called fourth constant, R equal to R0, delta R squared divided by 2, right? So this is the typical quadratic potential for the parabola of the harmonic oscillator, right? And then you have kinetic energy plus quadratic potential, and these functions are just functions of harmonic oscillator. Of course, this is a simple case of one coordinate. If you have more coordinates, then it becomes like a Hessian. Second order terms become generally like this. So it's a second derivative of energy, but respect to various coordinates, various nuclear coordinates. Right, but you could diagonalize Hessian and obtain the force constants along the so-called normal modes. All right, so then one thing to notice here is that this I index corresponds to electronic state, but there is of course multiple solutions, right, for the problem of the harmonic oscillator. We know that. So technically they just keep going up to infinity. At some point they become irrelevant because the surface is not harmonic, right? So then the true states become more like this, and then they saturate, and then they become a plane wave, right? Instead of being sort of localized, right? But this is like deficiency of harmonic oscillator problem. It's usually good here, not good at the high energies. All right, and this is all for a single surface. If you have now multiple surfaces far away from each other, then you could just consider this problem separately because the couplings that we ignored, non-adiabatic couplings, they are small if the surface is far away from each other, like this orbit, this energy levels, not levels, but the surfaces, they'd say, like in this case, don't cross. Here, it's one surface that dictates that the behavior of the nuclei, and here it's another surface, and you could, well, later we will talk about the time-dependent perturbation theory. With light, you could perturb the system, and sort of the picture usually is that light is fast enough so that it just takes the system nuclear wave function and puts it on a different surface. And now once we on a different surface, it evolves differently because technically we have for the time-dependent phenomenon, we need to solve this problem, time-dependent one, and we usually do that by okay, so we solve it in an electronic basis, of course, right? These surfaces are very useful for us. And then the nuclear problem becomes Tn plus the electronic potential of the surface where we are, right? And then chi, well, or whatever chi is, we switch to the electronic, we switch to the time-dependent problem. So this I a bar d over chi RT, that's the equation that governs the behavior if we get to the different surface. And yeah, that's the That's the usual. You could think of this as a usual time-dependent Schrödinger equation that you solve, like you may have solved in 1D problems. All right, so if you whatever potential you have, you could put the initial wave function and just by solving this problem, you could time-dependent variational principle, for example. You could evolve what the chi would be doing, and very simply, of course, there are multiple quantum phenomena, which is like whenever there is a bump in the potential, the function sort of splits, right? So part of it, why does function usually split? Because the function like this has multiple momenta in it, right? And so there are components that have low momenta, and then they feel that there's a bump, so they get reflected. And there are some parts that keep going, right? And so therefore you have what's called decoherence. Usually, decoherence simply means that you have these two that don't overlap anymore, right? So they just the wave function splits, starts moving. This is easier just to show in simulations, which people do. Now, if you could think of this on average like a classical wave function, right? So behaving, because classical mechanics works pretty well for the nuclear part, especially if the nuclei are heavy, right? So in this case, the wave packet will just go on this state and dissociates, right? Okay, so this is all more or less the dynamics on the single surface, right? So what I wanted to talk today mostly was about when the surface is crossing, right? So we go from the situation right here to the situation where we have potential crossing or avoided crossing. So those are the two scenarios. Like to give you an example. And then, of course, this is like the real situation. It turns out in diatomics, there's never crossing that will happen with the states of the same symmetry. With the states of the different spin symmetry, there could be crossing, but for the states of the same symmetry, there's always only avoided crossing. We'll talk why. Because people initially started looking at the diatomics, because those are smallest molecules, they thought that the surfaces never cross, because von Neumann come up with this rule. Neumann come up with the rule of non-crossing, and it was based on Neumann and Wigner von Neumann. Yeah, those are the two giants, Wigner von Neumann, a non-crossing rule. And this rule says that the surfaces, at least in 1D, the surfaces corresponding to the same symmetries, they never cross. And as it turns out, that when you go to the multidimensional systems, like say molecules like water, it already has 3 nuclei, right? 3 and minus 6 gives you 3 coordinates. Then there are crossings, which are quite common. So generally, the rule is for the crossings 3 and minus 8. And so if you have n equals to just 2, so then this is dimensionality of the crossing, because we'll talk this more in a moment. If you have multiple coordinates like hundreds of nuclear degrees of freedom, then 300 minus 8 is the dimensionality of the crossing C, right? But for n equals just 2, which is diatomic, 3 and minus 8 is negative, so you don't have crossing at all. Now, what's these curves? This is the case of sodium chloride, let's say, this is well, what sodium chloride is at equilibrium is ionic, of course. Sodium chloride, sodium plus, chloride minus, right? And when we dissociate sodium chloride becomes neutral. And this curve, the ionic curve, it's not the lowest anymore if we're just building it based on the fact that when we separate sodium and the chloride, we keep the charges. We can do that in the calculations, or we could just simply look at what the solutions of the electronic structure equation for the larger distances, right? We could see that okay, sodium chloride is ionic in the first excited state. And so then things like that. Now, if we excite the system to the neutral state, then the state kind of goes and split here at the avoided crossing. Why does it split? Because technically two surfaces become important in this area. So it's not anymore the equation like this needs to be considered, but more sophisticated equation with the couplings, of course. So effectively, whenever you have surfaces close to each other, you can think of that the forces that come from the potential of each surface. It's not the single force that is driving the dynamics anymore. You need to account for the different surface that is close, and you need to account for the couplings between the surfaces, right? So this Born-Oppenheimer picture, usually people say breaks down, because in Born-Oppenheimer picture, we are sort of thinking of the nuclei that are moving on the surface that is provided by electrons. Okay, so that's the general interpretation of this Born-Oppenheimer partitioning, that we have fast, it's like a classical way of saying this, the classical fast electrons, they create this manifold that is this electronic energy surfaces. And on that manifold, the fast manifold, the slow nuclei are moving, because it's almost like the pictures usually people provide, like a cow, which is slow, and the flies around it, which is quick. So flies are electrons, and they always well, adjust quickly to the nuclei, to the cow in this case. So, and they always will follow. Now, usually when we have one electronic state, one electronic cloud, the position of nuclei, if we don't supply too much energy to the system, it should be close to equilibrium. But if we say excite with light, then we disturb the electronic surface. We essentially switch the state of electrons, and for this new state of electrons, wherever the nuclei were, it's not optimal anymore, and so the electrons push the nuclei to a different position. Okay, so that's what is happening here in all the ultra fast, say, dynamics, which usually studied by lasers. If you do it fast excitation, then you go and disturb the electrons, and the electrons will push the nuclei to move somewhere else. Right, so that's how you could picture that. Now, how do we formally describe these areas for non-adiabatic processes, which could be with no crossing, or just it's called avoided crossing, the situations where the energies are close, or sometimes with a larger number of nuclei, so that it becomes a highly dimensional system. Now, you don't need to be too high. It's already with the 2 coordinates, that's enough. The surface will have usually the crossing, and the crossing is usually conical in the topology, right? So there's a crossing point, and this is like for the situation where we have two coordinates. It's not a physical situation because water molecule, say, has three coordinates. You don't have molecular case where you have two internal coordinates. It's always 3 or 1. But for considering the crossings, it's convenient to think about two coordinates because there it's just easy to draw, and it turns out with the y it's conical, and how does it appear to be conical? Why is it not like parabolic? Maybe in general, there are some situations like this, but in general it's conical. This can be shown. And to go a little bit forward, the reason it's conical is very similar to the reason why at equilibrium we have a quadratic. Why the surfaces near equilibrium point is quadratic, because the first non-trivial term in the Taylor expansion is quadratic here, but it turns out it's linear there, right? So we'll show that in a moment, but same math kind of the Taylor series expansion. And then, if you have at least two coordinates, then you can have intersections zero-dimensional, which is called conical intersections, and they play a big role in dynamics because we discussed, right? So if the surfaces come close to each other, the couplings that we neglected in Born-Oppenheimer, they diverge, and then it will become sort of you cannot ignore anymore the transitions. Okay, so let's just then consider what the nuclear equation will be if we have two surfaces that are close to each other. So we'll be talking about this equation, but this part is already known. We are writing this for the nuclear, nuclear wave function, and we're assuming separation of the. We're assuming the separation of translation and rotation, and we only consider the vibration of motion. So the equations in the basis of the electronic functions, one can simply write there is a sum over I, and you have phi j r h molecular. That's the starting point. Positive the H bar. Now write the time derivative simple form. It's equation 5 in the notes. Okay, so one note on the bracket notation, which is kind of interesting because it's tricky when it comes to the Born-Oppenheimer states. So usually for the quantum mechanics, if you write something like psi x in the as a ket, that would be wrong, because you're supposed to write x coordinate representation psi, right? If you want to write psi of x, if your coordinate is x, then the right way to do it is like this, right? Because the psi is a coordinate-less representation. Now, this would be wrong. Sometimes people do that without, simply, especially chemists, they sometimes make a mistake by using bracket notation just as a short notation for integral. Okay, so what they write is psi of r, let's say, let's say electronic dipole operator, and psi of r, and then maybe sometimes you put that it's the integration over r. that is happening. And maybe there is a nuclear coordinate here as well. They are talking about the electron nuclear wave function. So that's a wrong way to put it, because you have this Dirac notation needs to be like this. Now, for the Born-Oppenheimer separation, we have electronic functions that are parametrically dependent on nuclear coordinates, right? So these R's are not they're not variables, they're parameters. So the right way to write electronic wave functions, if you want to emphasize this as coordinate-less representation or using Bryan-Kett notation, of course, this is the electronic space, this bracket for electronic space. You already made a choice that you're gonna be using coordinate representation for nuclei, right? So then you will write for the nuclei either this, or you're supposed to then write it like this for the nuclei wave functions, right? And somehow make a distinction that this Bryan-Kett for the nuclear space and this one for the electronic space. So without doing too much of the trouble, if you wanna just use the Bryan-Kett notation for the electronic space, is the right way to imply that you're using it for electronic part like this. That's why I wrote it like this. And then you could also potentially write the electronic functions, I guess, that you have electron and nuclear, and then here we have a nuclear already determined, right? But then this is still sort of a function that is not, we haven't decided what's going to be for the electronic variables, right? So we decided that the nuclei already were R, but the electronic one could still be same momentum, right? If you want. But people usually go for the electronic variables, coordinate variables. Anyway, just keep that in mind. All right, so this equation, what does it lead to? It leads us to, for the case with two states, let's say, which are, we're just making up example where only two states which are close to each other, like here, other states are far away, right? And we are interested in dynamics somewhere in this energy region. By the way, why we like in the chemistry this Born-Oppenheimer separation, not only because you fix the nuclei electrons somewhere around, it's also because electronic energy scale is dominating. So that means usually if you are interested in a certain energy range, physics of a particular energy range, like your laser is red or blue or whatever, right? So then there are only a few electronic states that will be important. Others are not relevant, right? So then you could discretize the problem, like as I was explaining before, if you have a harmonic oscillator sort of kind of case where you have, say, two dimensions. One is very flat, like very shallow, another is very rigid, then you could use different number of basis functions for each, right? So the electronic, you have only, say, two states that are relevant, others are not. And that's great, because then you don't need to discretize electronic states all the way to the 100 electron volts. You could just say, all right, I am studying, say, vision process, and it's like few EVs. That's only two states, right? So what this will result in is sort of a matrix form like this. Plus So Hamiltonian that is acting on the nuclear wave functions, two components of two electronic states, chi1, chi2, and this is IT chi1, chi2. Right? So these are potentials, and these are kinetic energies as before, but now there are couplings. These tau couplings, what are they? Tau I j equals to -1, 2 mass of the nuclei, or mass of the mode, 2 pi I r first order coupling d over dr. And let's assume that for now, okay, so I guess later we will have R being multidimensional, but it's easy extension. So this is the first order coupling. Then there is a second order coupling. Both are not negligible if you have crossings or avoided crossings. Okay, so this is proportional to 1 over energy difference squared. This one is proportional to 1 over energy difference squared. Not squared, of course, just 1 over energy difference. Right, so these are the taus, and they peak close to intersection or avoided crossing, because these are still functions of dr. Okay, and they become important. Okay, so now what happens when the couplings are non-zero for this equation? You could think of it as if you initially say you put the state here, it will evolve based on this potential. This potential is not relevant because the energy difference is big. So it will evolve almost like classically sliding, or depends. Sometimes people say it's sliding because potential energy is reducing, but kinetic energy is growing. So the total energy is the same, of course. So sometimes people just draw that sort of like the wave packet is not really sliding on the surface, but rather go horizontal, right, with increasing the velocity. Either way, so it reaches the intersection, then it bifurcates, and then there are the components, let's say this is the second surface, chi2, and the component here becomes smaller. Part of it is transferring to the ground state, and then you can have two wave packets moving on different surfaces with different velocities. Once they separated, this one will move slower because of the uphill. This one maybe move the same speed or faster because it could be somewhat downhill, depends on the surfaces. But essentially there is no kind of connection anymore between them. And there's no, like, usually people talk in the quantum information again terms, because it's now coherent superposition, entangled, meaning that the really state that after this point is phi1 chi1 plus phi2 chi2, right? It's not really a product state anymore, it's a linear combination of products, so entangled superposition. But then there is no really any force that connects this with this anymore, because there is no like coupling here already. It could be small. It all depends on the taus, right? So the taus usually they peak here, and that's what stimulates the transition. But after they decay and then just this, if this wave packet indeed moves faster, it's already somewhere here, while this one is here, and overlap between them is zero, or become close to zero. So there is a natural decoherence of wave packets, nuclear wave packets, because the surfaces are different, have different profiles. Okay, so that's what coherence is really about. Is that different electronic states, they provide different forces for the nuclear wave functions. And there are multiple problems with the usual Schrodinger's cat paradox, right? One resolution, okay, you all heard about Schrodinger's cat, right? And then one can ask, okay, but seriously, what's wrong with it? Like, can we have a zombie cat that is half alive, half dead, according to quantum mechanics? And one outcome is that you could think of dead and alive indeed as a states, and they have very different dynamics of the atoms on a microscopic level. If you're dead, your atoms, like if you are dead, you are probably going to lay down and don't move anywhere, right? But if you're alive, you may go to the lecture or whatever to have some food. So the motion of atoms, the nuclei, is very different in those two states. So the state when the cat is dead and alive at the same time, it's this superposition state that will decohere very quickly, right? Because on the very many atoms, this situation, like the kind of the further evolution will be very different for those two states. Okay, and some people say, all right, yeah, sure, we can have dead and alive cat according to Schrödinger mechanics, but for a very, very short period of time, so short that it's not really relevant, right? Now, of course, what I like more as a kind of way to stop all this nonsense from the beginning is that to say that, well, one can say from the beginning that the kind of this whole problem is an open system problem. It's not quantum mechanics. Cat is not in a vacuum, blah blah blah. So it's not a closed shell or closed sort of problem that is subject to quantum mechanics. You need the density formalism and various environmental factors. But if you want to consider it even in quantum mechanical context, then the easiest resolution could be that, look, as they say, Schrödinger, I think himself made this mistake saying that, okay, well, there is a state of the alive and state of the dead cat, but those are not states of the Hamiltonian at all, right? So they are not eigenstates to consider dynamics in their basis. They are some superposition states. So then dead and alive, it's the moving states. And what happens here in the kind of general quantum mechanical sense is that you attached to one system another system, which is like this potentially decaying atom, right? So the potentially metastable atom is in this potential where it can tunnel and decay and create the, well, essentially stimulate the death of the cat. Sure, so then you have a not superposition, but tensor product of one state of the atom, now product state with the cat. State of the cat is a superposition, state of the atom is also superposition, because any metastable state is like just a superposition of eigenstates of the Hamiltonian that is like delocalized, and here it's like localized wave packet that will eventually tunnel. And so you just evolve one system by coupling it to another system, which is nothing surprising, yeah, sure. But dead cat or alive cat, it's not a state of the Hamiltonian. It's just superpositions. So there's nothing surprising. The same could be considered like, okay, if you have a gun and someone shoots you, so like one system could be considered also quantum mechanically speeds up evolution of another system, right? And that's it. So in a superposition language, everything is that is evolving is a superposition. A live cat is a superposition because it's evolving to the death and to the decomposition of the atoms or decomposition of the body, right? But dead cat is also a superposition because it just already moved halfway and then it just will start decomposing, right? So in that sense, they are both superpositions, and the whole thing is just a dynamics problem, which is not a problem at all because it's just evolving. Yeah. All right. So now let's think. How do we? I guess think about all this crossing and non-crossing problems and why conical intersections. Because conical intersections play a big role since there the couplets are divergent, right? So in order to see why conical intersections are prevalent and why they're conical, then we could introduce a new tool that is called crude adiabatic representation. So this is all was done effectively in adiabatic or Born-Oppenheimer representation, where the basis depends on the coordinate of nuclei, right? And that's why we have this non-adiabatic couplings, because our basis depends on the external parameter, which now becomes the variables, and then that's kind of a back reaction. The same we saw in the time-dependent problems. If we start to making the adjustment to the basis, which is then time-dependent. All right, but the nice alternative representation is this crude adiabatic representation. And before we get to that, just to give you just the general idea, since it's a very kind of prevalent in this dynamics beyond Born-Oppenheimer dynamics of multiple surfaces, is that to actually do this dynamics, the non-adiabatic couplings that you need to include in equations, they are quite unpleasant. They are divergent in the areas of the intersection. People try to avoid them because to do accurate dynamics, then you need you need integrals. You need these integrals, and then when you do the propagation, you need the integrals of this chi's represented as when you're moving Gaussians with these tau operators, right? So tau operators are not easy because they're spiky in certain areas, and then you need to integrate them over the big R's with the chi's, and that integration also not easy because you need a lot of points. If you are taking the integral with something that kind of divergent and the Gaussians, let's say, then the accuracy of sampling is important. Otherwise, you will get energy non-conservation, all sorts of problems. So how do people avoid that? Well, what they try to do is so-called diabatic representation. Diabatic representation, not diabatic, diabatic. It's just very frequently when I write something about this non-adiabatic in Word or other text editor that tries to change it to diabatic. It's diabatic. All right, so diabatic representation is the simple idea that why don't we try to find a rotation of these functions so that we remove divergences of these tau forms. And let's say we kind of we have a price that we're going to pay. We will allow these new functions. They're going to be linear combinations of these guys, some coefficients, and these coefficients, of course, are going to be R dependent. Otherwise, how we're gonna make change? Well, they could potentially be R dependent, right? But we will mix the adiabatic states into something that has a very like a small R dependence, so that there's this derivative couplings will be for the new functions not divergent, right? So one can think of in the context of the time dependence, we were thinking about the super adiabatic, right? But here it's based a little bit on the different principles. Conceptually, it's a similar story that we want some linear combination of adiabatic states that have non-divergent couplings. Turns out this cannot be done exactly for the finite number of states. Okay, for a finite number of states cannot be done because in order to zero these couplings, you need more coefficients than the equations you have to, like, essentially you will not have enough coefficients to zero everything that you need to zero in this situation with more kind of with a finite number of states. Kind of the easy way to see it is like you see here there is a quadratic number of couplings that you need to zero, but the number of coefficients you have will just simply not be enough because you also have you also will have a growing number of nuclear coordinates in general, right? So you need to zero all these guys for every derivative, not just for a one particular coordinate, right? So that's the problem. You just run out of the coefficients that you can manipulate because and that's the problem. Of course, there is more rigorous way of showing that, but that's the idea here. Now, turns out if you remove certain constraints, namely if you remove the constraint that the number of coordinates is not fixed, like let's say diatomic. For diatomic, the number of coordinates is fixed, and then turns out you can find the diabatic representation for finding the number of states, or if you say I don't mind that the number of states that I'm going to work with is infinite. Okay, so in those two cases, you can create diabatic representation, and you can remove these couplings exactly. So the crude adiabatic representation that I want to talk about to show the kind of this conical intersection on crossing rule, it's exactly the one way to do this by saying that, okay, I don't mind infinite number of my electronic basis functions. Of course, in practice, that is not possible. It's just convenient for various considerations, right? And you will see in a moment why. So the main kind of idea here is that why don't I just solve the electronic structure problem at a particular nuclear configuration? I will call it R0, right? So then R0, this is my electronic states. And because it's it's the Hermitian operator, observable even, like you could say that it construct a complete set of states for electronic degrees of freedom. Right, so then any function phi of R in electronic degrees of freedom, or any solution at a different R, you could write as a linear combination of the solutions at the R0. That's always possible because it's after all complete set. In electronic, we're doing this decomposition for functions in electronic degrees of freedoms, right? So if you solve the problem here, you can write the solution as a linear combinational. But for writing the, let's say, a simple example, writing the state of the, say, ground state at the R using the R0 here, you would not only need this function, but you need this function, this, so on, up to the infinity, right? You need infinite number of functions. And that is crude adiabatic representation. It is convenient because then the kinetic energy operator of nuclei cannot do anything to these functions, right? So these functions are not anymore, they have zero non-adiabatic couplings. Here, the derivatives are zero because functions don't depend on the nuclear coordinates. Okay, and then, but there is a price we're paying because this part, the matrix elements, which are coming from the electronic Hamiltonian, it's still parametric dependence on the nuclei coordinates present, and our crude adiabatic states, they will be only eigenstates of the Hamiltonian in a particular coordinate, nuclear coordinate, but not in any other, right? So then let's say if we consider the case for simplicity, we've still two states, just to not draw the infinite dimensional matrices. And you may ask, okay, but there's a problem. You want to do that with two states instead of infinite. It's not going to be very accurate, right? But I say, all right, the way I will kind of address this problem, let's say I want to study something that is close to intersection, right? And I will do it at the point where there's no intersection, but the surfaces are already very close. Okay, that's where I'm going to solve. That's where I'm going to put R0, right? In order to investigate what's going on here at the intersection, I will put R0 close so that I will only need just two states, and that the picture will be kind of nice, right? So that's the trick I'm going to play, so that I'm not going to go too far from the intersection to study it, and that will allow me to reduce number of states. Okay, then in that case, the representation will be accurate. Well, if it's not accurate with two states, I will come even closer to the intersection. Okay? That's the idea. So the kind of the equations then become like this. For the dynamics, it's the kinetic energy diagonal plus there is my states at the R0. I'll kind of skip the R0 argument, and then there's the electronic part for the R, and I will generally say R0 plus delta R near R0. This is the Hamiltonian, and then it's phi1, and then we have the same with the phi1, phi2, and then we'll have phi2, phi1, and then phi2, phi2, and then the pi one of the two, either time dependent or time independent. Let's say time dependent. Right, so that will be the picture in the crude adiabatic representation next near conical intersection, near intersection point. And then I can write that my solutions for the electronic problem, they can be phi I, the R, the normal one, R0 plus delta R. They will be sum over Ci j, phi j, R0. This guys depends on the delta R essentially. Right, so this is like coefficients that depend on the how far we are. And okay, in this representation, what we can do, not only solve for the chi's, but we can say, all right, what is the behavior of the kind of, we could investigate the behavior of potential energy surfaces, because diagonalizing this matrix potentially gives us this surfaces at close to the point R0, E1, E2, delta R, right, 0, 0. That's what we get if we diagonalize just electronic part, right? And the coefficients will be these guys, right? So this is our solutions, right? And my point would be to find what is the behavior of these surfaces after diagonalization as a function of delta R, right? We have behavior of each matrix element 2 by 2, as we could do Taylor series expansion here with respect to delta R, and that will give us the Taylor series expansion of this epsilon1, epsilon2, or E1, E2, and we'll see that these are conical, the equations for the cones, right? So that's the kind of idea here, because we could effectively, what we do, we start with the solution of the electronic Schrödinger equation at R0. At R0, where they don't cross, there's a gap. So at R0 plus delta R, it's a matrix 2 by 2. And if we do Taylor series decomposition to lowest order in each element, then we could have Taylor series decomposition of the eigenvalues. Okay, and eigenvectors as well if we want. Okay. Now, the only thing that we actually need is, let's just consider the Taylor series decomposition of the electronic matrix elements. They give linear terms as the first non-trivial, or not the quadratic, because we're not in any sort of minimum, right? So the Hij phi I R0 H electronic, which is let's say depends on R0 plus delta R by J 0 will be phi I R0 H electronic R0 plus delta R, then phi I R0 gradient electronic R, yeah, plus some other terms. Now, of course, these guys are delta Ij E I 0, and these are some some constants. So I have them as well, let's say number hij multiplied by delta r. And okay, 2 by 2 we can solve sort of exactly. Eigenvalue problem for. And it sort of becomes number h11. All right, number h11 plus, I guess, e1 r0 delta r or r delta r number h22 by 0 h12 1. That's the coefficients 1, 2. E the plus r right. So and then what we have is so this, right? The solution will be this is the diagonal elements, say call them h11 h22, this one h11, this one h12, so on. So then er plus delta r equals to h11 plus h2 divided by 2 plus minus root h11 minus h2 squared plus 4h2 squared. Divided by 2. Okay, so then this results in 1 plus 2 plus delta r number h11 plus number h22 minus difference becomes okay. Okay, so this is the solution, right? And what we can do with this, we could sort of invert the idea with the saying that, okay, if we actually looking for, if we start say at R0 where it's an intersection, right? That would be more convenient. Before I was saying that R0 could be placed close to the intersection so that we can study at intersection. Now I realize all this is actually more convenient to investigate the case where if the R0 is in the intersection, so then E1 and E2 will be the same, right? And what we want to see is that, okay, the lifting of the intersection. What is sort of this is the situation with like how the intersection is removed, right? If we have a multiple coordinates, then the cone structure appears as usually the equation like this: x squared plus y squared with a square root. That's the cone equation of say z, where z is a vertical, right? So then, if we put the R0 here as the intersection point, then these two are the same. That's just a constant, right? Then we have kind of 0 here for the E1 minus E2. This is the coupling part, and the delta R multiplied by coupling. So this is the analog of y squared. This is analog of the x squared, right? And we have kind of the square root of x squared plus square, like under the same square root of y squared, right? So that's the cone structure. And usually there is a difference in delta R that are surviving for the H1 delta H12 and the delta H11 and 22 because the integrals here for the different states they essentially coupled by different coordinates in the molecule than the ones that for the diagonal states, right? So that if you have symmetries, if the states of the electronic states are the same, then the coordinates usually that makes this integral non-zero are different than the situation where these electronic states are different. Okay. And so that's why these delta r's, they become different coordinates under this square root in the case of non-diagonal chords and off-diagonal chords. Also, we could see that in order to have a kind of in order to have zero degenerate, like essentially in order to arrive to degeneracy, we need two conditions in general to satisfy. One is that off diagonal couplet, like the diagonal terms, they should be the same, and the off diagonal terms should be zero. And in that case, this will be sort of well, for any delta r, this will be a zero with the same diagonal, essentially the degeneracy. And those are the two conditions that you need to satisfy, and the only things that you can satisfy it with is the nuclear coordinates. So then it becomes, if you have 3n-6 coordinates, in order to have a degeneracy, you need to use at least two coordinates to satisfy these conditions of the same energy difference, same energies and zero couplings. So that's 3n-6 goes to 3n-8 for the case of general system. In case of linear systems, it's 3n-5 goes to 3n-7. So that's how we get that for diatomics, even if it's n equals 2, still there's no possibility to zero the coupling with the coordinate. So in diatomics, you don't have a crossings. That's why it's usually what's called non-crossing rule. But then for larger molecules, there's always possibility to find the crossings. It's just crossings are always there. It's just they're not always relevant. That's the thing with the crossings. Now in the typical kind of scenario for the crossings is either we have something like this that is more the, okay, so usually it's more like the upper state is less rigid. So let's say it's somewhere like this, two surfaces. And this is more the situation of fluorescence, when the system stays here on the, say, S0. This is S1, this S is corresponding to the spin, singlet spin usually. So you excite vertically, and the system is just doesn't have enough energy to reach the intersection. Okay, so that means it usually fluoresces back. Okay, just because of the coupling with the field. Now, another situation is where you have something like this. So then you excite really on the slope, and the system kind of moves towards the intersection. And this could be an isomerization. This is going back. This is staying on the excited state, and eventually somehow either through crossing with other states or maybe fluorescing. Depends. But usually, if there is a channel, you end up in a lower state, and that all that energy that is coming from light is transferred to heat. Right? So those are the two kind of situations. All right, more systematic, I guess, description in the notes. Any questions? Yeah.
You describe the two-dimensional case, right?
Yeah.
But what if it's a three-dimensional case? Will it be a hyperbola? What kind of shape will we have in that case?
In the three-dimensional case, like water case, this is going to be 3 atoms, water, right? So 9 and 6, that's a three-dimensional internal, like the 3 vibrations. And there's a conical intersection but 3 and minus 8 means it's 1. 9 minus 1, or minus 8 is 1 for the water case. What this means is that the space, well, that's why people like two-dimensional case. It's possible to draw it because you use two-dimensional. The third one is energy. So in this water case, you need 3 dimensions: x, y, z, z, and then 4th dimension is energy, and this crossing is the line. Right. So why did you jump to hyperbola?
No, because I was just looking at the pattern in which the slope of the line was decreasing. So, I mean, initially it was parabolic, then it was linear. So I assume that would be something like x to the power 2 by 3. So
We're talking about different things then. I was talking about the dimensionality of the intersection, right? So in this case, 2 lines or 2 curves intersect in a point, right? So point is 0-dimensional. Now, in the surface case, the conical intersection dimensionality of the crossing is in 2-dimensional. It's 0, it's point. In the 3-dimensional, it's a line, and 4-dimensional is the plane, like some sort of 2-dimensional surface. It could be of any sort of form. I don't know. Like it depends on the. Yeah, you cannot just simply say that it's going to be in a certain functional form, because you need to consider hypersurface of 0 coupling and the same energies essentially, right? So those are the 2 conditions. So, and if you know how the energy behaves as a function of the R and how the couplings behave as a function of R, then you could say what will be the surface of the intersection. But generally you cannot say, because only locally you could say that the degeneracy is listed linearly. But how does it behave locally? Maybe you could say from the gradients of the energy difference and the couplings. But in general, it's like the same as saying we know that the quadratic, like say harmonic oscillator, is a good close to the equilibrium. But how does it behave after? That's you need to do calculations. All right, see you, I guess, next Tuesday.